We're solving problem 15 from the 2025 AIME1. Let n denote the number of ordered triples of positive integers a, b, and c such that a, b, and c are less than or equal to 3 to the power of 6, and a cubed plus b cubed plus c cubed is a multiple of 3 to the power of 7. Find the remainder when n is divided by 1000. So for this problem, we mainly have two cases. What we want to do is split this into cases, if there are any, and then add those cases up to get the total number n. So that's exactly what we can do. So we have a value x, right? If 3 divides x, then that means x to the power of 3 is equal to 0 mod 27. Now if 3 doesn't divide, this would still be just congruent to mod 3 or mod 9, because it is multiple of 3. So just mod 3, I guess. And then there's the case where 3 doesn't divide x. If 3 doesn't divide x, then this means that x has to be congruent to either 1 or 2 mod 3. Should probably change this one to mod 3 then, just to make things clearer. So, therefore, for this case, x cubed would be congruent to 1 or 8 mod 3. Now, basically, we have three numbers, and we want the case such that a cubed plus b cubed plus c cubed is equivalent to 0 mod 9. And so for this case, the ways we could have this or this right here. So what this is basically saying is that to be mod 3, we can either do 0 plus 0 plus 0, or we could do 1 plus 8 plus 0. This is 9, and it is divisible by 3. And this is basically pointing toward this case over here. So we know that there's already two distinctions drawn out here. So we can call these type A and type B. So let's just say this one's type A and this one is type B, where type A is basically when all the numbers are multiples of 3, all multiples of 3, and then this one, there's only one multiple of 3, and the others are not, but two of the numbers have to match. So we call this one type A and type B. Now n is simply type A, the number of triples that satisfy type A, plus number of triples in type B. So we can just keep on going down with this. So we let A be equal to 3A base 1 base 1, B equals 3 B base 1, and C equals 3C base 1. Now, we know that A cubed is 27 times A base 1 to the power of 3, so we can take out that 27. And then we are left inside the parentheses A base 1 to the power of 3 plus B base 1 to the power of 3 plus C base 1 to the power of 3. Now we know that this entire number has to be divisible by 3 to the power of 7, because this is divisible by 3 to the power of 7. So if 27 is 3 to the power of 3, then this has to be at least divisible by 3 to the power of 4, because that's what's left. Just going to write it out. A base 1 cubed plus B base 1 cubed plus C base 1 cubed has to be divisible by 3 to the power of 4, which is equal to 81 in this case. Now, with this newfound information, you can start multiplying things together, multiplying powers of 3 together to start solving for the number of type A's and type B's. And by doing this, this is something you shouldn't do in a competition, but it's like a more rigorous method, I'd say. By multiplying continuous powers of 3, right? We find type A is equal to 531,441, 531,441. Type B has 254,294. So we know that N is type A plus type B. And this huge number, when we sum these two, well, obviously, it can't be our answer, right? Because, first of all, AIME requires all answers to be integers through 1 to 1,000. So we have to do mod 1,000. So basically, all we care about is these last 3 digits. So if like you carry the 1 for a new place into thousands, just don't do that. But you can just add these last 3 digits for both of them, and then you'll get that we have an answer of 735 when you add these two together, these two big numbers together, and then do mod 1,000. So that's our answer that we have.